Okay, let's look at example 1 here, our first actual example of a real projection. We're going to take this vector in R3, the vector 4, 5, 6, and W is just going to be the x1, x2 plane, the xy plane, because it is spanned by the vectors e1 and e2. So the set of all linear combinations of these two vectors. And V is going to be in that column space, in the x1, x2 plane, because it is a linear combination of the e1, e2 vectors. And in particular, the scalars are going to be these fractions here. And what we're going to do is we're going to show that this is actually the projection onto W of the vector y. So let's start by finding V. So we're going to do something times E1. But what are we multiplying times E1? We're doing E1 dot y. So if we just match these up, we're going to do 4 times 1, 5 times 0, and 6 times 0. So that will just give you 4 divided by E1 dot E1. But E1 dot E1 is just going to be 1 because it's 1 squared plus 0 squared plus 0 squared. So that's 1. And we're doing that times E1. And then adding to that the same thing with E2 and y. So E2 dot y, the top of this, is 4 times 0, 5 times 1, and 6 times 0. So that'll just be 5 divided by the denominator. E2 dot E2 is 0 squared plus 1 squared plus 0 squared, which is 1. We're multiplying that by E2 here. So this is V, and 4 times E1 is, of course, just going to be 4, 0, 0. And 5 times E2 is going to be 0, 5, 0. When you add these up, you get 4, 5, 0, like so. And yeah, that is a vector that is definitely on the column space of E1 and E2. It's in the subspace W here. And maybe it seems a little intuitive that that's going to be the point on the x1, x2 plane that is closest to 4, 5, 6. Now, let's find y minus v and check that that is actually orthogonal to W. We want to show that that is actually, that this V here is actually the projection onto W of y. But first, let's get the y minus V. That's going to be 4 minus 4 is 0. 5 minus 5 is 0. 6 minus 0 is 6. And yeah, I'm doing that in red because that's like the vector that goes from the subspace W up to y. That's like the orthogonal component of y. That's orthogonal to W. But let's check that because we want to see, is that y minus v orthogonal to W? Because what it means for v to be the projection onto W of y is that v is the unique vector in W that makes it so y minus v is orthogonal to the subspace W. That's what the definition is. The y hat that makes this work is the unique vector that makes that y minus y hat in W perpendicular. Meaning it has to be orthogonal to every vector in W. So if you do y minus v dot producted with E1, that's 0, 0, 6 dot 1, 0, 0, you definitely get 0. And likewise, if you do y minus v dot e2, you still get 0. So yeah, y minus v is orthogonal to the two vectors that span W. So that means it's orthogonal to everything else in W. So we're going to see that this formula is a general way to get projections. It turns out it doesn't always work if you just have any old vectors that make up a basis for your W. It turns out they need to be orthogonal to each other for this formula to work in general. And we're going to show that in a minute. But first, let's talk about orthogonal lists. Because like the list of vectors E1 and E2, we're going to see is an orthogonal list because it satisfies this definition. A list of non-zero vectors, U1 through UC, is called an orthogonal list if every vector is orthogonal to every other vector in the list. In other words, that ui dot uj is equal to 0 if I is not equal to j. And if all of the vectors have length 1, like they're normal vectors, we call it an orthonormal list. So the standard basis of R3 with just the regular old I, j, k vectors, E1, E2, E3, that's an orthonormal list because E1 dot E2 is of course 1 times 0 plus 0 times 1 plus 0 times 0, which is 0. And same thing with any other pair of them. So that makes them orthogonal to each other, and they're normal vectors because they have length 1, right? Like E1 dot E1 is 1 times 1 plus 0 times 0 plus 0 times 0, and that means that the length of E1 squared is 1 squared. So the length of E1 is 1. Okay, let's do an example here where we have this 4 by 3 matrix. We have 3 different columns that are all R4 vectors. And we want to show that this is an orthonormal list of vectors. All right, so what we need to show is that what we just did here. We want to show that U1 dot U2 is 0, U2 dot U3 is 0, U1 dot U3 is 0. And to be normal vectors, we want the length of each one of the columns to be 1. So that means U1 dot U1, which again is the magnitude of U1 squared, that should be 1. Likewise, U2 dot U2 should be 1, and U3 dot U3 should be 1. So yeah, if all of these are 1, that's the normal part, and if all of the dot products with non-matching ones are 0, that's the orthogonal part. So let's calculate these. So yeah, U1 dot U2 comes out to be 0. So here you can see U2 dot U3 comes out to be 0. Then if we do U1 dot U3, that should also be 0. And it is 0. Okay, so it's orthogonal. Are they normal vectors? Are they length 1? Well, if you do u1 dot u1, you get 1/2 times 1/2, which is just going to be 1/4 plus 1/2 times 1/2 plus 1/2 times 1/2 plus 1/2 times 1/2, and that gives you all 4 quarters 1. And the same thing will be exactly true with the other ones. It's just that you have something negative that when you square it, like when you do negative 1/2 times negative 1/2, it still becomes positive 1/4. So that's also what you get when you do u2 dot u2 and when you do u3 dot u3. So yeah, they are all length 1. Cool. So we have an orthonormal list of vectors. Let's see what happens when we multiply this by its transpose in both different orders. So first, let's do u times u transpose. So taking this first column and turning it into a row gives you that. I'm going to do the same thing with the second and third columns here. Here's the third column turned into a row of u transpose. So let's just use the row column rule to multiply this out. This is going to end up being 4 by 4. The first entry here is going to be the dot product of row 1 of u with column 1 of u transpose. That's going to end up being 1/4 plus 1/4 plus 1/4, which is 3/4. Moving on to the next one, you end up getting 1/4 because 2 of them end up canceling out. In row 3, we get 1/4 again. And in row 4, we get negative 1/4. Going on to column 2, we get 1/4 here, and we'll just continue. Phew, that was a lot of fourths there. We got a pocket full of quarters here. So, one thing to notice about this is that this is actually a symmetrical matrix. In other words, if you take row 2, that's 1/4, 3/4, negative 1/4, 1/4, that is the same as column 2, just transposed. And that's true with any other row or column. Like row 1 is the same as column 1. That's actually going to be really important in chapter 6 when we look at symmetric matrices. So it's equal to its own transpose. All right, let's see what happens when we do u transpose times u. That's actually going to be more important for this section. And this is maybe the more interesting one. So I'm just going to write this here. Here's u transpose. Here's u. Now, when we calculate this out, there's a nice shortcut, which is that, like, if you wanted to find the row 1, column 1 entry here, we'd be using row 1 of u transpose dot producted with column 1 of u, right? So we're just doing u1 dot producted with itself here. So maybe we can just write it out that way. Like, we know that u transpose, its first row is the transpose of column 1 of u. Its second row is a transpose of column 2. and its third row is the transpose of column 3. And we're multiplying that by u, which is just u1, u2, u3. And still just using the row column rule, this is going to be u1 dot u1 in the first entry here. The second thing here is going to be u2 transpose times u1, which is really just u2 dot u1. The third thing, using row 3 of u transpose dot producted with column 1 of u, which is u1, that's just u3 dot producted with u1. And if we do the same thing for all the rest of them, and all of the things in the second column, we're just doing dot products of the various rows of u transpose with column 1 of u. So for the first one, that's u1 dot u2. Then we have u2 dot u2 here. Then for the third one, that is u3 dot u2. And in column 3, it's the same thing. It's just u1 dot u3, u2 dot u3, and u3 dot u3. Like so. Now, what do we know about all of these dot products? Well, let's zoom out a little bit. Let's look up here. We found that u1 dot u2 is 0. So maybe I can highlight in green all the ones that should be 0 because these are orthogonal. So that's u1 dot u2, we did u1 dot u3 was 0, and u2 dot u3. But dot products are commutative, so u1 dot u2 is the same as u2 dot u1, so these ones should also be 0. And then what else did we find? That because they're normal vectors, length 1, that all of their dot products with themselves are equal to 1. So u1 dot u1 is just the length of 1 squared, which is 1, same with u2 dot u2, and u3 dot u3. So what does this give you? Everybody's favorite matrix, the identity matrix. The easiest matrix to do anything with, maybe other than 0. Now, the fact that this came out this way, it wasn't anything special about this orthonormal list in particular. It's just the fact that it's orthonormal. The fact that it's orthogonal means all of the dot products of some of them with other ones are equal to 0. And because it's normal, all of the dot products of them with themselves come out to 1. So this is going to be true for any orthonormal list of vectors. And that is exactly what theorem 5.10 says. If U is a matrix with orthonormal columns, then U transpose times U is equal to I. So we basically just proved that in the last example. To prove it, if you have a longer list of orthonormal vectors, works basically the same way. So anyways, now it sounds like a good time to take a break. We'll look at theorem 5.11 in the next video, which is basically going to be proving that the way we did this in example 1 works in general. So I'll see you then.